Welcome to this video in our course on process control and optimization. And in this video then we want to talk about the components and their concentration in the system. So our basic objective might be to say, after having an expression for how to control the level, now we want to be able to characterize what concentrations of the different species do I have. So maybe say we want to characterize concentrations of species. And then we have to look into our model building procedure again. The balance volumes we already have. So this is done. The second step then is the specification of the characterizing variables, so two. And here again we have our states. Now the relevant state we have to consider actually is the concentration of our substance I. Then we have the inputs, which could be the temperature, if we assume it's controlled, and which could be the direction volume V, which is provided by our level control. And then we have also our input streams, with also the concentrations of the different species in this input stream, and this is for the both of them. And as an output, we might be interested in CI actually directly. After that, we look into our model building procedure. The next step, balance equations. So 3. And the balance equation we might want to consider for that is the amount of a species in terms of moles. So the change over time of my species in the system is what is going in through fluid 1 plus n dot I in 2 minus what is going out and I out. And then we have also to consider what is happening by means of reactions. So then we again look into the transfer rate specifications and say 4. We have again our flows. So Ni in 1 equals the concentration in the input flow, Ci in 1 times V in 1. Then we have Ni in 2 equals Ci in 2 times V I in 2. And we have the same for the output, and I out equals Ci out times V out. Then we have to deal with this reaction term as well and say, okay, what is this? This is NIR. And this can be described by the reaction rates of the different reactions and stoichiometric coefficients. So we have J as an indice for the reactions, and we have the stoichiometric coefficients, nu I, J. multiplied by the reaction rate, Rj, multiplied by the reaction volume. And now the question is, what is Rj? Rj can be, in example, described by means of a reaction constant, Kj, times a product of the different concentrations in the system, Ci, to the power of the order of the reaction in terms of this component. So it's a little bit, maybe a little bit confusing, but I hope you can grasp it. And then we have the reaction constant, Kj, for reaction J, which then could, in example, equal and be described in terms of an Arrhenius equation, which is based on one more constant, K0J, times the exponential function independency of the activation energy of reaction J divided by the universal gas constant times the temperature in the reactor. And then if we look again into our modeling workflow, then we have the property relation specification. And here we say again that the hold up Ni is the product of the concentration and reaction volume. And we could also say that Ci out equals Ci, which is a very common assumption. So what is actually the concentration in here is assumed to be what is coming out here as well, which makes sense in most cases. So, and now we all have again all our ingredients at hand to combine them together and derive our model equation. So this means then dNi dt equals dCi times V dt. And now we have to consider the product rule for the derivative and say Ci is dV dt plus dCi dt times V. And now we have to remember what is dV dt. We learned it in the last video, and there was this equation that said dV dt is equal to V dot in 1 plus V dot in 2 minus V dot out. And this we can reuse now and plug it in. And if we then go up here and also consider these streams, we get the following equation, dCi dt times V plus Ci, and then we get in this one V in 1 plus V in 2 plus minus V out equals, and then we get our right hand side from up here with C in 1 times V in 1 plus Ci in 2 times V in 2 minus Ci out times V dot out plus our reaction term, and we leave that one as it is right now. And afterwards we can like reformulate this and put this stuff on the other side. So if I subtract this term from this term, I will see, under the assumption that Ci and Ci out are equal, which I assumed here, that this term diminishes. So we have the negative term here, we have it here, so it goes out. And we get a difference for each of the volume flows, V in 1, between what is going in and what is in the tank. Furthermore, if I then divide this volume on the right side, I get the following expression: dCi dt equals, and now we have here our V in 1 divided by V, and we get the difference Ci positive, Ci in 1 positive minus Ci, so Ci in 1 minus Ci, first term. Then we have the second one, which is V in 2 divided by V, and again we have the Ci in 2 minus Ci. And then our whole reaction term is coming, because, as I said, this is diminishing. Now we have to deal with this NRI. So we take this term, plug in the reaction rate, and in the reaction rate we plug in the term for the reaction constant, and we get, yeah, kind of a little bit more complicated term, which denotes as the sum of the reactions, J, with our stoichiometric coefficients, nu I, J, times the reaction constant, K0J, times the exponential expression, minus EIJ divided by RT. And this then times this expression for the concentrations Ci gamma I J. And this equation is our relationship of the term we wanted to know, like the Ci, and what we are putting in, like the volume, the temperature, and also these inputs, and therefore characterizes this relationship. So, and this is it for this video. Thanks for watching, and we see each other in the next one.